Welcome students. Today we'll start a new chapter, chapter 10, Wave Optics. In today's class we'll discuss wavefront and Huygen's principle. In previous chapter we have assumed that light travels in a straight line. Using this concept we have explained reflection, refraction, dispersion. Now the question arises whether the light really travels in a straight line. Consider a light source illuminating a screen. If we place a coin in front of the light, the coin obstructs the path of the light. If the light travels in a straight line, then we should see a dark circular spot on the screen. However, this does not happen. In fact, we get a bright spot in this place. This can only explain if the light bends at this point and reaches this part. To explain this bending of light, in the year 1678, a Dutch physicist, Christian Huygens, proposed a theory called wave theory of light. When a stone is dropped into a stagnant water of pond, water spread out from the points of impact in a concentric circles. Every concentric circle is associated with either a crest or trough. Crest is the above part of a wave and trough is the lower part of the wave. All the points on the circle will oscillate with the same phase. This is because they are at the same distance from the point of impact. A locus of all this point or the circle made out of all these points which oscillate in the same phase is called a wavefront. The speed at which the wavefront moves outwards is called the speed of the wave. Now draw a tangent at a point on the wavefront, then a line drawn perpendicular to the tangent at that point is called a ray. The ray is in the direction along which the energy of the wave travels. Christian Huygens applied the same theory to the light and proposed that light travels in the form of waves. A point source generates spherical waves in 3 dimensions. Similarly, a line source like fluorescent tube and linear slits will generate wavefronts that are cylindrical in shape. A plane wavefront can be produced by any source located at far distance from the source. Best example is the plane wave which arrives from the sun. At large distance, a small portion of spherical wavefront appears to be a plane wavefront. Now, if we know the shape of the wavefront at time t equals to 0, using Huygens principle we can easily determine the shape and the position of the wavefront at a later time. Let us consider a point source S. The source S generates a spherical wavefront AB traveling away from S. Now according to Huygens principle, each point along the wavefront IB is the source of a new disturbance and a spherical secondary wave originate from these points which spread out in the forward direction. These secondary waves are called as wavelets. If we assume that the medium is isotropic medium means the medium where all the physical properties will be same in all the directions. The velocity of the wavelets will be same in all the direction. The radius of the secondary wavelet is given by r equals to vt. Now, if we draw a tangent to all these waves, we will get the position of the new wavefront a dash, b dash. When time t is equal to 0, the radius of the secondary wavelets will be equal to 0. It represents the initial position of the wave when the time t is equal to tau. Tau is any random time value. The radius of the secondary wavelets will be equal to v times tau, and this will be the new position of the wave. In the similar manner, we can determine the shape of the wavefront of a plane wave going through a medium in forward direction. Fine. So that's it for today's class. Thank you. And if you have any confusion, please don't hesitate to ask. I will re-explain it to you again.